All right, so now let's move on to data analysis for solution calorimetry. And this one uses data from last year. They did a run with tris, with 0.507 grams of tris and a calcium chloride dihydrate in water dissolution. So this is the data they got last year. Okay, so this is how you would analyze the data. So mass of the tris from this experiment was 0.507. Initial temperature is given as 22.0909 degrees Celsius. The final temperature, if you recall from your calorimeter, it doesn't give you the final temperature, it just gives you delta T, right? So we kind of have to switch these things around. We put our delta T here. Instead of calculating delta T, we're going to put the delta T as given by our calorimeter, 0.295. And so what would be our final temperature? It will have to be a formula in this case, right? Initial temperature plus that. Yeah, initial temperature plus delta T, right? Just this. So final temperature is the initial temperature plus delta T. What's our mean temperature? Again, how do you calculate mean temperature? Equals the initial plus 0.63, which is 1 minus exp to the negative 1. 63% of the delta T, right? And delta T is 0.295. So your mean temperature, or you have 63% rise during the reaction, is 22.27. Should be between the initial and the final. Yeah. Okay. The Q for the reaction of tris with HCl is known. And what is it? It's in the handout. It's also in the manual for the calorimeter. So let's look it up from the handout. Let's see. Let's look at the handout for the formula for Q. Solution calorimetry handout. Right here. This one right here. Okay, so Q is equal to mass of tris times 58.737 plus 0.3423 times 25 minus the mean temperature. So let me type that in. So Q for solution calorimetry. Q for the tris reaction. Standard run using tris plus HCl. The number is, what was it? Mass of tris minus, it should be negative because this is an exothermic reaction. Mass of tris times 58.737. 58.737. Okay. Plus 0.3423 times 25 minus the mean temperature of the reaction. This is in calories. Okay. Now, notice that what happens if the mean temperature is 25? Then this whole term here just drops out, right? So it's really 58.7 calories per gram of tris that's being used in this experiment. So tris is your limiting reactant. So let's go ahead and enter that formula into our Excel sheet. It's a little smaller so I can copy that formula. What's our formula for Q for tris? So this is equal to minus the mass of Tris, which is V5. It will start with minus, it will work as a formula as well. Times parenthesis 58.737 plus 0.3423 times parenthesis 25 minus the mean temperature, which is 22.2774. Close parenthesis one more time. That's calories. What would that be in joules? How do you convert calories to joules? One thermochemical calorie is 4.184 joules. Times 4.184. So minus 126 joules. So what's our calorimeter constant? Our calorimeter constant, our Q, is going to be equal to minus C cal times delta T. Okay. In the standard run, we don't know C cal, we do know Q. And we measure delta T. So we can solve for C cal. C cal is what? The calorimeter constant is, so minus Q over delta T. So let's see. This one? That's just the value in joule calories times 4.184 joules. Okay. So Q divided by so calorimeter constant is equal to minus C cal, minus Q divided by delta T, which is this one right here. So 429 joules per Kelvin. Okay. Is that a reasonable number? How much water did you use in your run, in your aqueous solution? 100 grams, about 100 mils. 100 mils of water, what's the specific heat of water? 4.18. So what's the heat capacity of 100 mils of water? 418, right? So why are we getting 429? It's not just water, it's something else in there, right? So a little bit extra. It's mostly due to water, the heat capacity of the calorimeter and its contents. All right, so let's do the delta H for the dissolution of their compound. They use calcium chloride dihydrate, so CaCl2.2H2O. The mass of their sample was right here, 1.4702. And the molar mass of calcium chloride, what is it? Dihydrate. Molar mass of calcium chloride dihydrate. 147.01. 147.01. So how do you calculate moles of sample? B17 over B18. Mass divided by molar mass, 0.01. And that's basically what I've told you in the instructions, right? Make a solution, 100 mils, that's approximately 0.01 molar, 0.1 molar. So 0.01 moles divided by 0.1 liters is yeah, should give me 0.1 molar. Okay, what's our initial temperature? It's right here, 21.5564. What's our final temperature? It's not given by this calorimeter because it gave you delta T. So let's put our delta T here, which is 0.8351. So how do I calculate final temperature? Add delta T to that, to the initial plus delta T. Yes.
Does it matter? I just noticed it. Does it matter that the delta T is in Kelvin?
No, because when you subtract temperatures in Celsius, you get the same answer if you subtract temperatures in Kelvin because your 273 will cancel out. All right, so is this reaction exothermic or endothermic? Well, you can use an if statement here. If delta T is negative, let's see. If delta T is positive, the temperature went up. Is the reaction exothermic or endothermic? Exothermic, so I put in quotation mark here, exothermic, comma, and then otherwise it's endothermic. And this should be an exothermic reaction, right? I'm sorry? This one says if the cell above, delta, which is delta T, is positive, then you're looking at an exothermic reaction. Otherwise, it's an endothermic reaction. Okay, so we can see that this reaction is endothermic. Exothermic. The temperature went up when you dissolve calcium chloride dihydrate in water. C from the standard run is 429. So I'm just going to point to that. If you have several standard runs, point to the average, okay? Don't point to just this number, which is what you're going to have with your lab data. You'll have several standard runs, so you probably need to add another row here with the average and point to that instead, okay? So standard run times delta T is what? That's just a C for the standard run, right? Or you can make this a formula for the average of the different runs up there. That might be an easier way. So you can say this is average of, let's say you did multiple standard runs, you can average these several runs like that. Okay. Okay. You could have just done, let's say, equals average. Let's say you did 3 standard runs, then you say this run, this run, this run, and then this run, and then this run, maybe. Something like that. All right. But since you only have one, I'm only showing you one standard run here. Just use the number for that one standard run. If you want, I can make this average of B12. That way you remember next time that that's really an average of several numbers. Okay. So what's our Q in this case? Minus C cal times delta T, right? So equals minus C cal times delta T. That's our Q. So that's the delta H for the actual run. What's the delta H on a per mole basis? Divided by the number of moles, but I want it in kilojoules. Divide by 1,000. Minus 35.82 kilojoules per mole.
Okay. Can you scroll up?
Which one? Which one? This one? Q is minus C cal times delta T. And delta H is the actual Q divided by the actual number of moles because you want it per mole. But you divide by 1,000 because I want it in kilojoules per mole. Okay? Pause this or stop this.